let's see, so two boxes, one heavier than the other, initially at rest on a horizontal frictionless surface. You have the same constant force that acts on each for 1 second. Which has more momentum after the force acts? So you have the same force F here that acts on the light and the heavy box. Which has more momentum? All right, let's stop at 1 minute. 1 minute. Just guess if you're not sure. Let's see, C is the right answer. Remember, this goes back to our Newton's second law. Newton's second law is F equals dp dt. So if I have the same force that acts on both boxes in the same amount of time as they do in 1 second, they're going to have the same change in momentum. Remember, this is just a rewriting of Newton's second law. It's actually the original way he wrote it. dp is m dv over dt, which is mass times acceleration. In the previous question, which box has the larger velocity after the force acts? The heavier one, the lighter one are both the same. They have both the same momentum since they have the same force over the same amount of time. So which box has the same or has the larger velocity? The heavy, the light one are both the same. Stop at 35, 35. Okay, good. B is right. Um, Again, going back to Newton's second law, if I have F equals dp dt, they both have the same change in momentum, but momentum is mass times velocity. So the one with the lighter mass will have the bigger velocity. They both have the same momentum, but the one with the smaller mass will have the bigger velocity. A small beanbag and a bouncy rubber ball are dropped from the same height above the floor. They both have the same mass. Which one will impart the greater impulse to the floor? Remember, impulse is just change in momentum, so it's just a fancy way to say change in momentum. Which will feel the larger change in momentum when it hits? The beanbag, the rubber ball are both the same. Okay. I'll stop at 40 seconds. 40 seconds. Okay, let's see. Remember, our change in momentum is mvf minus mvi, assuming that the mass remains constant, as it usually does. Uh, and so here I have a rubber ball that goes down. This is its vi. It goes down, and then it bounces back up again. This is its vf. This is the rubber ball. The beanbag, on the other hand, it goes down, it drops, and then it just stops. So its vf is equal to 0. So let's try this again. We're sort of all over the board. So which one of these has the larger change in momentum? The ball or the bag? The ball goes down and bounces back up. The bag drops down and just stops, the bean bag. Okay, doing a little better. I'm going to stop at 30 seconds. 30? Stopping at 30. Okay, B is the right answer. We talked about the rat tail, right? The towel, popping people in the butts with a towel, right? The same idea occurs here, that when I have a recoil velocity, when I have a rebound velocity, I have a greater change in momentum. The towel experiences a greater change in momentum when you flick it off. So similarly here, the rubber ball experiences a greater change in momentum because this term is not zero. My VF is not zero. And notice too, you have to consider the signs. My V initial is negative, so it's going to make this positive here, and this is also positive. So if I have a recoil velocity, my momentum goes up a lot. So the right answer is B here. A person stands under an umbrella during a rainstorm. Later, the rain turns to hail, although the number of drops hitting the umbrella per time and their speed remains the same. So basically, you're just taking the raindrops, and instead of being raindrops, they're now ice drops. They have the same velocity, same mass, all that business. Which case requires more force to hold the umbrella? When it's hailing, raining, are the same in both cases. Think about how the hail is different from the raindrops. When the hail strikes your umbrella, how is that different from a raindrop striking your umbrella? I'll stop at 50 seconds. 50? Okay, good. Why is it more difficult to hold the umbrella when it hails? What does the hail do? It bounces off, right? So the hail bounces off, imparting a greater change in momentum. Did y'all hear about when White Tigger had his head stuck in the toilet? This is like a fourth grade joke, first of all. White Tigger had his head stuck in the toilet. He was looking for poo. I'm sorry, that's kind of gross, but it's a fourth grade joke. Fourth grade little boy joke, right? A bowling ball and a ping pong ball are rolling towards you with the same momentum. If you exert the same force to stop each one, which takes a longer time to bring to rest? Remember our Newton's second law, F is dB/dt. I'll stop at 45. Okay, so we have the same momentum here. My force is dp dt. They both start with the same momentum, so this change in momentum is going to be the same. They start with the same momentum, they both end with zero. I exert the same force on each of them, so which one requires what's the right answer then? If I have the same momentum and the same force, how do their times differ? How do they differ? Or do they differ? They do not differ, right? So B here is the right answer because I have the same force, same change in momentum, so dt is also going to be the same. That change in time is also the same. All right. A box slides with a velocity of 10 meters per second. It collides inelastically. Remember, inelastically just means that energy is not conserved, but momentum is conserved. The boxes stick together. That means it's what type of inelastic collision? It's a perfect inelastic collision, perfectly inelastic. What is their final velocity? Initially have VI, this one. The other block is at rest. I want to know now what is VF. Stop at 55, 55. it's not 10 meters per second. It is E, 5 meters per second. Because make sure that you're up to on doing these. You're going to have collisions on your test coming up on Wednesday. But you say that the initial momentum equals the final momentum. The initial momentum is m times vi. I'm not going to include this one because it has a momentum of 0. And the final momentum will be 2m times vf. 2m, just because now I have both of these moving, so I just say m plus m, which is 2m. Let's see, I can get rid of my m's here, and so vi is twice vf. That means vf is going to be half of vi. So vi was 10, so now vf is 5. Okay. We'll come back to this. We'll look at some more collisions in just a bit. Uranium nucleus at rest. It's not moving, has no momentum. It splits into two fragments, one heavy and then one light. Which fragment has the greater momentum? So this uranium nucleus is here. It splits into two pieces. This one flies off in that direction, this one in this direction. Which one has the greater momentum? The heavy one, the light one, the same momentum, or can you not say because you don't know various things about it? All right, I'll stop at 50. 50. What is the momentum of the particle before it splits? It has zero momenta. All right, zero momentum. So that means after it splits, the two particles together have to have the same momentum combined because momentum is conserved. All right, so here, uh, this has zero momentum, and then down here, they're going to have the same magnitude of momentum. They're going to be equal but opposite, but have the same momentum. So C is the right answer. They both have the same. Which has the greater speed? I already said they have the same momenta, the light one and the heavy one. Which one's going to be going faster? The heavy one, the light one, the same speed, or can you not say? Well, I'll stop at 40. Stop it at 40. Okay, awesome. B is the right answer. The light one, they have the same momentum. Momentum is mass times speed or velocity. And so the one with the smaller mass has the bigger velocity. Amy is 150 pounds. Gwen is 50 pounds. They stand on slippery ice and push off each other. If Amy, who weighs 50 pounds, goes off at 6 meters per second, what speed does Gwen have? It's a lot like the uranium nucleus splitting off. All right, I'll stop at 55. Just 5 more seconds. All right. If Amy slides, do I have their names? Oh yeah, I'm sorry. Sorry. Yeah. So E is the right answer. Sorry, I got their names wrong up here. Sorry about that if that misled you. So this is Amy. and this is Gwen. Um, so the initial momentum is 0, and that's going to remain constant. So I have the initial momentum, which is 150 times her speed, Amy's speed, which is 6 meters per second, or negative 6 meters per second, plus 50 times Gwen's final speed. That has to equal 0. So VF is 3 times 18 meters per second. Cannon sits on a stationary railroad flat car with a total mass of 1,000 kilograms. You fire out a 10-kilogram cannonball, speed of 50 meters per second. What is the recoil speed? A lot like both the problems with the uranium nucleus and with Amy and Gwen. What is the recoil speed of the flat car? Pretty well so far. Most of you have the right answer. All right, I'll stop at 105, 105, 105. B is right. Very good. So here my initial momentum is equal to 0, and that's going to equal the final momentum. That means that the cart, the 1,000-kilogram thing, and the cannonball are both going to have the same momentum. So after the cannonball comes out, its momentum will equal to the momentum of the cart. So I know then that the mass of the cannonball, that's 10 kilograms, times its speed, which is 50 meters per second, will equal to the mass of the cart, 1,000 kilograms, times its final speed. So that's 500, so VF equals 0.5 meters per second. And it's going to be to the right, because this one has a momentum in this direction, this one will have a momentum in that direction to the right. So B is the right answer here. When a gun is fired, the bullet and the gun have equal and opposite momenta, then why is the bullet deadly, whereas it's safe to hold the gun? So they have your gun and your bullet both have the same momentum. Why then are they so different? All right, I'll stop at 50 seconds. 7 more seconds. And C is right. So they have very different velocities because their masses are so different. The gun has a much bigger mass than the little bitty bullet, so the bullet goes a lot faster because they have equal and opposite momenta. But their energies are a lot different. So because energy is 1/2 mv squared, and I have this squared term, this quadratic term for the velocity, since the bullet has a much higher speed, it has a whole lot more energy than the gun. The bullet has a lot more energy. All right. All right, folks, let me run over the exam right quick. It will be uh, on Wednesday. We'll be in the auditorium like we usually are. I'll hand out the exam at 7:15, so recommend that you get there. It'll still be the same length, even though you have a take-home portion, but then you just sort of have more points spread across more questions. So that's good for you. I think there are 5 questions. One is just sort of a short answer, write one sentence kind of question. and then the others are calculations. One of them is a very simple calculation, and then the others are slightly more involved, meaning more steps. Um, you're going to have the take home, and let me just reiterate, I sent an email out about this, but your take home is an elastic collision, like we worked in class last time. If you weren't here last time, you can find it on the screencast. You can look them up online. If you Google for about 5 seconds, you can find elastic collisions, and you can even find calculators. If you want to put in the numbers, that's fine, and just make sure that check your answer with what you find elsewhere. You can use whatever resource you want on a take-home portion of the exam. On the next exam, we'll have take-homes as well, so uh, they're just sort of slightly more complicated problems that I wouldn't put on a test. Just a lot of algebra, really. The concepts are pretty straightforward for the elastic potential, or the excuse me, yeah, the elastic collisions. Remember, you're just setting the momentum initial and final is equal, and the energy initial and final is equal. So it gives you two sets of equations, so you can solve for both final velocities. So it's really solving a system of equations. Your problem is very similar to this. Um, I want to see you solving the system of equations. Also, if you fish around online for about 5 seconds, you can find solutions to the final velocities. Please don't use those. I want you to actually solve the system of equations. So where you solve one equation and substitute it into another. You follow what I'm saying? If you Google online, you'll find, well, V1F is equal to M1, blah, blah, blah. Please actually solve the system of equations. Okay? You'll turn that in on Wednesday when you come into the exam, and that's worth 10 points on your exam. You'll have 15 multiple choice, and there are, as I said, 5 free response. You have different classes of problems, two sort of big classes of problems. We have conservation, well, not two, we have more than two. Conservation of energy, like for example, when we have a cart on a track or whatever, and I ask you what is the velocity at particular points along this way. Uh, that's only when you have conservative forces acting like gravitational forces. We also had the type of problems where we have, a spring, and I have an object moving with a certain velocity, and setting equal the kinetic, or considering the kinetic energy and the elastic potential energy. That's that 1/2 kx squared. We also have the work done by non-conservative forces. So the work done by a non-conservative force we found is equal to the force times dx, the integral of f to f dx. Uh, we did some problems in class where and you have one in your homework as well, where you have to figure out what is the work done by a non-conservative force, and we will need to do that as well. So finding the force due to a path-dependent force, where the force is dependent upon the path, is non-conservative too. Um, so conservation of energy, either gravitational potential energy, elastic potential energy, where you have conservative forces at work, or both maybe, where you have a spring and like a track like this. You'll have a force that is position dependent or path dependent, where you have to actually solve for the work that's done. I would look back at your homework. We worked an example in class for that as well. Um, of course, you'll need to be able to do a dot product. So remember, if you don't remember, go back and make sure that you're up on your dot products. Uh, where I'll give you the force in vector notation. I'll give you the force, the distance, or the displacement in vector notation. Just be able to find the dot product of that. You could see some of the other things worked into that, where if I have work, describing the energy of that object, remember that these concepts of work and energy are closely related. That if I do work on an object, I change the energy of that object. I can take away energy, I can give it energy, I can change its potential energy, I can change its kinetic energy. So you have problems like all of those. Let's see, I think you had one, two, I think you just had two problems based on those ideas. Okay? So that was sort of the first part. In the second part, you have momentum. In momentum, I have really sort of two classes of problems. Conservation of momentum problems. These are collisions between two or more bodies. You'll just have two bodies. You will have a two-dimensional collision. It'll be an inelastic collision, so energy will not be conserved. you have an elastic collision in your take home, but you're having an inelastic collision, two bodies, two dimensions. So two bodies, two dimensions. I have tried to make it pretty simple by just making you respond with vector notation, which if you look back at the problems that we worked in class, it's a lot easier because you don't have to deal with the magnitudes or the angles of the vector. So you're just dealing with the vector notation. So make sure you go back and that you can do a 2D collision with an inelastic collision. Okay? We can look back, if you want to look back at some of those, we can in just a bit. You also have Newton's second law, F is dp dt. These are, if I have a change in momentum, m delta v over delta t. If I have this change in momentum, it means that a force is acting. We work through a problem, it's like the car colliding into the wall. If you have the collision time and you know the change in velocity, then you can figure out what is the force imparted to that object. Um, need to know the difference between elastic and inelastic. Elastic conserve momentum, energy, or both. They conserve both, right? Elastic conserves both uh, energy and momentum. That includes anytime you have field forces that are involved, gas particles, charge particles, where they come together and they bounce off one another, but they don't actually touch. So elastic conserve energy, and a good example is like the collision between gas particles. Inelastic conserve only momentum, and that's everything else. Bumping into somebody, hitting somebody, whatever, is an inelastic. Cars colliding, that's an inelastic collision. So those are a few different questions on the test. Like I said, there were 5 total. So, all right. I don't want to say it's an easy test, but it's probably the easier test of the semester. So I want y'all to do really well on it. If you're thinking about dropping the class, this is sort of a key test because drop day is on Friday. I really want you to do well in this test so you can see that you can stay in the class and do well. Okay? What do y'all feel you have questions about? Taylor? The take home is worth 10 points. And then the free response is worth 50 or 55, and then the rest, 35 or 40, is in multiple choice. I would look back at your concept test, look back at the old test, the conceptual type questions. There are actually a couple of simple calculations, one step, easy numbers on the multiple choice as well. I think I actually put a perfectly inelastic collision on, and maybe one other one. Y'all want to work through some problems? Look at some old exams maybe? All right. We'll use the rest of this time to sort of review over. We're not going to go into the next chapter, but we'll use the rest of this time to review over some old tests and just sort of look at some things. I'll just pull up some old exams. Let's see. Let's look at last semester's exam 3. All right. These are some good ones. Something similar to this. So I have this particle is on a frictionless track. It's initially at a height of 10 meters and traveling at 4 meters per second, and the particle's released, or it moves. So I want to know the speed of the particle at point B, which is 2 meters high, the speed of the particle at point C at ground level, and then how high does it move off to the right when it comes to rest. I want to think about what types of energy I have. I have both kinetic and potential energy here. I know it has kinetic because it's traveling at 4 meters per second. And then at point B, I also have kinetic and potential energy. I can set both of these equal to one another for part A. I say that 1 half mv squared, I'll go ahead and put in the speed there, it's 4 meters per second, plus m times g times h, which is 10 meters, that's this value, is equal to 1 half mv squared plus m times g times this height, which is 2 meters. Notice that my masses, they all cancel. I can divide through. That's always going to be the case unless you're dealing with a spring, and then the masses won't cancel because your spring is not, the elastic potential energy isn't dependent upon the mass. It's only the spring constant. So I have 16 plus 100 equals 1/2 v squared plus 20. And then we can solve that 116, that's, oh yes, yeah, you're right, 8, I'm sorry. And then so that's 108 minus 20, 88 times 2 is equal to v, which is whatever it is, doesn't really matter what the number is. But that's how you would solve it. You should have a problem like that. You will have a problem like that. Hopefully that's a gimme problem that you can go through and do that. Well, hopefully, gosh, I hope they're all gimme problems because we've worked through problems that are very similar to everything that you'll see on the test. All right. But you have to know how to do those. So, but I think that y'all are capable. I think that y'all can do well, like do really well on this test. All right. So, what is the speed of the particle at point C? So, at point C, what type of energy do I have? I have only kinetic because H equals 0. Potential energy equals 0. So I only have kinetic. So I'll work it exactly the same way as I did at part A, except I'm going to not have potential energy. So I'll just repeat this side of the equation. I have 8 plus 100 equals g, or excuse me, 1/2 v squared. You see what I did there? I skipped a couple steps. This was, I wrote mgh plus 1/2 mv squared equals 1/2 mv squared. The m's all canceled out, and then I'm just left with this here. This is 8 times 100. That's this plus this here, here, equals to 1/2 mv squared. Can you write out all the steps? Okay, let me write out the steps here. So I have uh, the total potential, the total energy over here, that's 1/2 mv, which is 4 meters per second, squared, plus m times g times h, which is 10 meters, equals the kinetic energy down here, 1/2 mv squared. The m's cancel. I'm left with 8 plus g times 10 is 100 equals 1/2 v squared. So it's going to be the square root of 216 equals v. Right. And then on the last part, I'm not going to work through it here, but on the last part, you're setting this energy equal to the energy of the object over here, where it's only going to have what type of energy? Kinetic or potential or both? Only potential energy over here. So it'll work out very similarly. I'll just say the kinetic energy plus the potential energy from here equals the potential energy from here. You have a couple homework problems that are similar to this, so make sure that you can do conservation of energy with conservative forces. So nothing funky going on with the forces. They're conserving energy. Can I take this away? All right. Now, we'll also have a position-dependent force, and you have a spring too, actually, to let you know. Don't forget Hooke's law too, in case you need to calculate the force due to a spring. I don't think I mentioned that, but we did go over Hooke's law. That's F equals kx. If you know the spring constant and you know the compression or elongation of the spring, then you can find the force. Okay, so it says a spring has a spring constant of 100 newtons per meter. Mass of a 2 kilogram block, you compress it, causes it to move to the right and continue on a frictionless surface. I want to know the velocity of the block after it leaves the spring. Well, to do that, I would say 1/2 kx squared, which is the elastic potential energy, is equal to 1/2 mv squared. So all that potential energy in the spring is converted into kinetic energy. And I would solve then for v. See the halves I can divide out. V is the square root of kx squared over m. I know k, it's right here. I know x, it's 10 centimeters or 0.1 meters. And I know m, which is 2. So that's how I find v. And then I want to find how far the block travels. So as it travels, it encounters a force that's equal to negative x to the 1/2 power, a resistive force. Now this is a non-conservative force. I know it's non-conservative because it's taking energy away from the object. You can think of it as friction, but here it actually changes with time. And what I would do, if I want to know how far does it travel, well, I set the total energy of the block, which is 1/2 kx squared. This is a half of 100 times 0.1 squared. 100 is the spring constant. 0.1 meters squared, that's the amount that you've compressed at 10 centimeters, which is 0.1 meters. I'm going to set that equal to the integral of negative x to the half dx. And then I'm going to integrate over 0 to xf. And I'm looking for xf because it want to know is how far does the block travel. Xf will be the block's final position. All right, so I can integrate this. It's going to be x to the 3/2. That's 1/2 plus 1 divided by 3/2, which is going to be 2/3. If I bring, so it gets a 3/2 in the denominator, and I flip it up, it becomes 2/3. And this is going to equal to this value, whatever that is, 50 times that 0.01, is that 0.5? Is that right? And I solve that for x. Because my initial position is 0, I just get xf right here. I solve that for xf. Make sure that you can deal with a position-dependent force. Practically every test that from here on back the past 4 or 5 years has a position-dependent force. So look at those and make sure that you can do it. We did it in class. It's in homework too. Be sure that you can do that. Simple integrals, just polynomials. If you're not clear on how to do those integrals, please come see me. But you just add 1 to the exponent, and then you divide that by that value. Okay? Will be on the test. Shall be on the test. Can I clear this? Okay, the other big things are, well, you will have to do a dot product too. So just to recall, right, dot product is just f dot d. I just want to know the work done by the force. F dot d is 3I minus 5j divided with 2I plus 1j. Remember, on my dot product, f dot d is equal to fd cosine theta. That's our definition of a dot product. These are vector quantities. These are the magnitudes of those vector quantities. If the two vector quantities are in the same direction, cosine theta is 0, so that's equal to 1. If they're perpendicular to one another, cosine 90 is 0. Is that what I just said? If they're in the same direction, cosine of 0 is 1. If they're perpendicular to one another, cosine of 90 is equal to 1. Is 0. If they're in the same direction, the dot product's 1. If they're perpendicular, the dot product's 0. So when you're doing your dot product, you just take similar terms. I just say 3 times 2, negative 5 times 1. And I lose all the vector notations because remember a dot product is a vector or a scalar product. It's a scalar product. We'll get into vector products next chapter. Alright, so I do 3I times 2I, 3I dot I, minus 5j dot j. But I dot I equals 1, j dot j equals 1. So it's 3 minus 5, negative 2 joules. Yes, you're right. I'm sorry. 6. 6 minus 5, which is 1 joule. You will have to do a dot product. It'll be just a few terms like that. So just looking for doing FOIL out and then leaving out those that aren't similar. So leave out the j dot i's, the j dot k's, all that stuff. Okay? And then it goes on here. I'll let you look at this on your own, but I could ask you other questions that have to do with like the work energy theorem. If I do work on this object, what happens to its energy? Ask about its velocity or its potential energy or a number of other things. All right, let's look at momentum stuff because that's all from chapter 5. Let's see, this test have it? Oh yeah, so you will have a two-dimensional collision. So on this one, I have these particles. It's going to look very similar to this, y'all. Similar figure, I just changed the positions and the velocities and stuff. So make sure that you can do a two-dimensional inelastic collision. Two-dimensional inelastic collision, our initial momentum equals our final momentum. Uh, Here, our initial momentum is only with this particle. This one has no initial momentum. So I say the initial momentum is the mass, 1 kilogram, times its velocity, 4I minus 1J. And that has to equal to the final momentum, which is going to be the momentum of this particle and the momentum of this particle. They both start moving after the collision. So it's going to be 1 kilogram times negative 3I minus 2J plus 3 kilograms times V2F. And I'm looking for V2F. It's going to be in vector notation. So whenever you're doing this, you just keep all your i's together and you keep all your j's together. So up here I'd have 4I minus 1j equals 3I minus 2j, negative 3I, plus 3V2F. And I solve that for V2F. I get 4 plus 3, that's 7I. Brought this over here, adding it up. Bring this over 2. That's 2 minus 1 is plus 1j equals 3 V2F. And then I divide through by 3. Sorry, I can't scroll up. So I get divide through both sides by 3, and I get 7/3 I plus 1/3 j is equal to V2F. So that's how you report it in vector notation. As I said, I'm not going to have you report it the magnitude and direction. I think y'all can do that, but you would just use the Pythagorean theorem and the inverse tan to find the magnitude and direction. You will have a problem with a 2D collision. Take this way. All right. Make sure that you can do a 2D collision. It'll be very similar to that. You probably have one like this. I'm not sure yet, but this is applying Newton's second law, F is dB/dt. I want to know the magnitude of the force acting on the ball. dP is the change in momentum, m delta v over delta t. I think this was straight from the homework, actually. Um, Mass is 0.15 kilograms. The ball speed is 6.5 before impact, and after is 3.5. I always like to draw a picture. So before, it's going down at 6.5 meters per second. Notice it's negative, and then it goes back up at positive 3.5. This is VF. You gotta watch your signs on this, so just be very careful with your signs. It's going to be 3.5 minus negative 6.5. It's minus because this is VF minus VI, and notice that VI is negative initially. So watch your signs. That's really sort of the trickiest part on these problems, is getting your signs right. Divided by the change in time, which is 0.1 seconds. So this becomes 10, so it's 1.5 over 0.1, which is 15 newtons. Okay, that's everything that we've done in the past couple chapters, and it'll look a lot like that. All right, folks, any questions? Feel fairly straightforward? I feel comfortable with this test? think many of you could probably take it today and do okay on it. So, but again, some of you really need a good grade on this test. So let's make a good grade on it. Y'all come see me if you need help. Any questions? We'll call it a morning. Um, yeah, that doesn't affect y'all. Okay, y'all have a good day. Okay, I'll see you later.